Yesterday we said AI first cuts text into tokens. Today we ask the next question. After a token becomes an id, how does the model compute with it? The answer is embedding. Intuitively, it places a token onto an invisible semantic map. Think of city coordinates. Beijing, Shanghai, and New York are not paragraphs on a map. They are positions. Words can work in a similar way. Cat, dog, and pet tend to live near one another. Car, rocket, and invoice live somewhere else. This map is not two-dimensional. In real models, one token often becomes hundreds or thousands of numbers. That list of numbers is an embedding vector. It is not a human definition. It is a coordinate the neural network can use. How do we get it? Inside the model, there is an embedding table. Imagine a huge contact list. Each token EDA points to one row in that table. Picking up that row gives the token its vector. So yesterday's pipeline becomes complete. Text becomes tokens, tokens become ids, ids look up embeddings. Are those coordinates written by humans? No. The beginning of training, they are mostly like notes scattered on a wall. The model solves tasks, makes mistakes, states its parameters. Rows in the embedding table are pushed into more useful positions. Why do cat and dog become close? Because they often appear in similar contexts. Both can eat, sleep, pets, and appear near words like cute. Here is a tiny three-dimensional toy example. Cat is high on the animal direction, high on the cute direction, and low on the vehicle direction. Dog looks similar to cat. Car looks different. Car is high on the vehicle direction and low on the animal direction. Now for a small calculation. Multiply matching coordinates from two words, then add the results. That gives a similarity score. Cat and dog get a higher score because many directions line up. Cat and car get a lower score because their directions disagree. This calculation is called a dot product. You do not need to memorize the symbol yet. It asks whether two vectors point in similar directions. Another common version is cosine similarity. It cares more about direction and less about the length of the vector. That is why search systems can use embeddings to find related content. Compare semantic coordinates, not just exact words. Large language models do something similar at the input layer. Each token first receives its embedding vector. But that is not enough. The same word can mean different things in different sentences. Bank can mean a financial institution or a river edge. So, an embedding is more like an initial identity card. The transformer later rewrites the token state using context. This matters. Embedding is not final understanding. It is the computable representation that understanding starts from. It is also not a dictionary. A dictionary gives humans definitions. An embedding gives the model a position it can compare and update. Yesterday's tokenization answers which piece is this. Today's embedding answers where should this piece live in semantic space. Tokens are language blocks. Embeddings put coordinates on those blocks, so the model can notice which blocks often belong together. Later, when we talk about attention, RAG vector databases, and recommender systems, this idea will keep coming back. Many AI systems begin by turning text, images, users, or products into vectors that can be compared. So remember the simple version. An embedding is the bridge from discrete symbols to continuous coordinates. AI does not directly hold meaning in its hands, compresses meaning into numbers, then computes relationships among those numbers.